Hello, this is a video going over problem 2 from the final exam from spring 2021. Problem 2 focuses on applications and phase diagrams, and so that's going to be the focus of this problem here. For this phase diagram, you're given two curves that you have to develop. The upper curve that's shown here, that is we use a linear regression for. So we see that that's defined there. For the lower curve, we have three different sets or up to more or less of those multiple regressions that we're going to develop for that one. Row 1 and row 2 would go to set 1, row 3 and row 4 would go to set 2, 5 and 6, and so on if we have more regressions than that. These are the set of x and y values we would use to determine the exponential regression for our lower line. So immediately this is very similar, or thinking about that live, the problem we did with the live lecture where we had multiple regressions we were moving through. So following the tasks that we're going to have below, we want to develop a code that creates a phase diagram that looks like below. That's a good visual to remind ourselves, and determine which phase diagram results in the largest liquid region. So we're going to need to figure out which of these regressions result in our area for liquid being the greatest. Using that phase diagram, we're going to determine where we'll then allow the user to enter points until a point is entered for the liquid phase. So they're going to enter values until a point is entered in the liquid phase. At that point, the code will end. So we'll follow the task to kind of develop this code. You see that we define liquid as in between the upper and lower regression, inclusive, meaning on the line is liquid. Mixed is below the lower regression and in between the higher horizontal and vertical line. And then the gas, the gas is an entire other portion of the phase diagram out here. So task 1 is to create a code that determines the linear regression. That's just a quick application of polyfit. Then for each set of lower data, we need to determine the exponential regression and determine the two intersection points. We want to output to the command window the two intersection points and the appropriate set number. The horizontal line is based on the first intersection point. So where this horizontal line or the y value of this horizontal line is based on where this intersection occurs, and the vertical line, this x value, is based on where that second intersection occurs. For each lower data regression, determine the area of the liquid region and store the area for each set in a vector and export the final vectors of the area as a .csv file. This should run whether we have 5 sets, 10 sets, or 1 set. And so in order for our code to be flexible, we don't want to just repeat our code 3 times because we have 3 sets. We need to make this code work regardless of the number of sets we have. It's going to find all of these results and output those areas as a .csv file. So that's going to require repetition, require us to move through each of those lower regression sets and determine those results. At this point, we haven't plotted anything. We're simply just determining the area and determining intersections. Task 1 is very much a polyfit anonymous function application. Task 2 is where we get to the plotting and the phase, and task 3 is the phase determination. So we'll start with task 1 and move to MATLAB and develop this code. So we're gonna need to load in our data. Both of our data points are our upper and our lower, and determine our linear, and then create a loop structure that will determine the exponential. That way it runs once, 3 times, 1 time, 2 times, however many. So I'm gonna start with my upper. I'm gonna read in my problem to upper.csv and go ahead and apply my polyfit for my linear. So this is something that you should be able to easily do. I have my X values, which are the first row of upper. I have my Y values, which are my second row of upper. First order. I have my M1 equals linear 1. My B1 is equal to that second value. You don't have to break this up, but I like to break it up. And I can create a function handle for my linear, which I can call my linear EQ and that's just my M1 times X plus B1. For it to be an equation, I need to create my independent X variable. So that should be easy. Creating a linear regression should be really easy. For this one, for the next part, it might be overwhelming thinking, how do I do it for multiple regressions? Let me do it for one, and then I'll add the repetition accordingly. So for sure, I'm gonna load in my lower data. And for now, I'm just gonna go ahead and call my X values lower 1 and my Y values the second. I'll figure out how to move it to the third and the fourth, the fifth and the sixth, and so on with that repetition. So doing that, I can then apply my polyfit. I'm going to use my I'm going to say exp1 is equal to polyfit. When I apply my polyfit to these X and Ys, X stays the same, but I need to take the log, the natural log of Y first order. And then when I pull out my M value, I'll call this M2. My M is just the first. My B value is going to be the EXP of the second value. I can then create my equation. I'll call this EXP equation. My EXP equation is going to be B2 times EXP of M2 times X. No dot multipliers are needed in either of these cases. EXP already works element by element. Remember, do not do e to the power of. MATLAB's not going to know what you're doing there. Now that we've done this, we're going to be trying to find intersection points at two locations, one close to 1 and one close to 9 on kind of either end of the spectrum. You'll notice in this problem, when you look back at the problem statement, we specify one occurs near 0 and one occurs near 9. We give you the starting point for applying F0. But before we do that, we need to create our difference function. Our difference function is looking at the difference between our two functions. That means linear EQX minus EXP EQX. Two different intersection points. I'll call this I1 for my first intersection point. F0, I'm going to look for the one that's near 0. So diff 0. For I2, F0, I'm going to look at the one that's near 9. This represents the range of those two values. If I want to find the area between these curves in this range, this is just a quick application of integral. My area is equal to integral. The area between the two is my difference function between I1 and I2. So now I've done this for one regression. I need to see how can I add repetition in order to do this for two regressions. Well, what's increasing each time is the row here. This needs to go to 3, this needs to go to 4. And so if this is going to 1, 3, 5, and so on, I'm going to create a for loop that's going to go from, I'll call R1 by 2 to the number of rows I have in this data set. So I'm going to find out, say row is equal to the size of lower comma 1. And it's going to go to the number of rows. That means this is going to be set by R. It's going to go 1, 3, 5, and so on. This needs to be 2, 4, 6. So this, just kind of similar to the last problem, needs to be R plus 1. We'll smart index that. Everything else in here stays the same. It's based on this X value, so I don't need to change anything else in here. The only other thing I need to change is I'm trying to keep track of all of my area values. So I'm going to create a counter that starts at 0. And each time I run this loop, I'm going to increase that count by 1. And that's going to help me move to the next position of area. So the area is going to increase in size each time, 1, 2, 3, 4. I don't want to use R here because R is going to go 1, 3, 5 and kind of skip, and I'm going to have zeros mixed into that. I need to have a unique counter because of how I've set up my for loop here. What's not in here is an fprintf statement that would create the output you would see in the sample output, because it's going to sample output the equation for each set. So count can act as the set number. So you could also use this as set. We need to add fprintf with count and equation. Oh, sorry, and intersection points. I leave that to you to do. When we look at our task 2, our task 2 is now to determine the set that results in the largest liquid region. We have a vector that does that, so we can just take the max. That's going to help us do that. And use the data for this set to create the plot for our phase diagram as some blue solid lines. So we're going to plot everything. You notice that I tell you plot between the two intersection points. Your horizontal line is based on the Y value of that first intersection point. The vertical line has a X value based on the second intersection point. And you're going to hard code that axis range for our phase diagram. That's typical for what we would do with a phase diagram. So when we go to MATLAB, if I want to know which area was the maximum, I'm going to ask for the max area. I also want the location. That location is going to tell me which set, 1, 2, 3, 4, however many I have, had the highest. So max area, location is really important, because location is going to tell me which X and Y values I need to use to develop my phase diagram. In this case, my X values are going to be, I'm going to pull from lower. The row that I want is LOC times 2. let's say it's the second set. That means I want to do 2 times 2 would be 4 and go back 1. That would get me to the third position. You want to use indexing in this case. If you try to use a set of if statements, no matter how you do it, you're going to hard code. So you want to make sure to do it this way. My y value is lower. I need my y values would come from the fourth if let's say the max occurred in the second. That's just times 2 all the values. This does require me to redefine my equation and determine that equation. So I'm going to redefine that here and make sure that I'm using the correct, based on my x and y values, the correct coefficients and the correct exponential curve. I also need to pull out the correct intersection points. So I could just repeat the calculation I did here. I could have also tried to store my intersection points as a vector, just like I stored my areas, and pull out using that index. Either one would have been fine. I'm just gonna, because I have the code here, recalculate. So all of this stuff ends up being recalculated based on the index here. Once I have these values, I just need to f plot appropriately. So I'm gonna hold on at the beginning, so everything on here goes onto the same plot. I'm gonna f plot my linear EQ. My linear EQ, and both of these are gonna go from I1 to I2. Our blue line. I'm going to copy this. Oop, I have an extra parentheses there. I need to do this for my exponential curve. And then I also need to do the plot for my horizontal and vertical line. For my horizontal line, my 2 y values are going to be the same. My x values are going to range from the first intersection point to the second intersection point. And my y values are going to be the same. It's going to be where that intersection occurred. I could choose either of the equations, linear EQ I1. So where that intersection point occurs, I put it into either function that represents the y value. For the x value, my x is going to stay the same. This is my I2. The y values are going to go from whatever the y value was for my horizontal line to the y value of that second intersection point, I2. So you kind of have to think through visually how to set up these horizontal and vertical lines. They're based on these intersection points, and they're also based on putting these x values of these intersection points back into your function to determine the y values. For our phase diagram, we always want to put in our axes. So in this case, it tells us to hard code them as -6, 12, 0, 180. We're gonna do that there. So some of the tricks with this, what really the biggest trick was figuring out kind of how you were going to index out and find that, not just find the area, but how you were going to then redetermine and apply the correct stuff to your phase diagram, and then really thinking through how you wanted to set up your horizontal and vertical line. The last task is where we're determining the phase. So we want to use the phase diagram above, that phase diagram we just determined, and ask the user to enter a point and determine the phase, gas, liquid, mixed, output the phase point. We want to keep prompting the user to enter a point and plot the point on the graph after each entry until a point is entered for the liquid phase. Once a point is entered for the liquid phase, the program should end. So our limiting factor in this case is not a menu that's asking the user to enter a value. It's simply, once we find a liquid, we're then going to stop our program. So when we go back to MATLAB, I'm going to first set this up so that it works for one point, and then we're going to add that repetition. That's going to be the easiest way for it to address this. So for one point, I'm going to call this user point. I'm going to have the user enter in a point, enter point. They're going to give us an X and a Y value. For that X and the Y value, for that X and Y value, I want to know what is the predicted value for my linear and exponential line based on that X value. I'm going to go ahead and determine that at the beginning. So I'm going to call this what I'll call my predicted linear. And I want to apply my linear equation by putting in the user point, the X value. And my predicted EXP is going to be using my EXP equation. I'm going to put in that same X point. So this is just going to give me the predicted point so that I can know whether it's above or below each of these lines or in between, right? Because that's so it tells me whether it's liquid. So I'm only worried about whether it's in between these, in between the two intersection points. If it's outside of these two intersection points, it's gas. So my first question is, well, if my X value, my user point 1, is less than or equal to I2, and that user point is greater than or equal to I1, then I have a set of questions. Then I'm not sure if it's liquid, gas, or mixed. Otherwise, it's gas. And I can have my gas output and plot point as green. Now, if it is in between that, I got a lot more questions, right? Now I want to know, well, if the Y value, I need to know more about this Y value, is less than or equal to that linear predicted value, and it is greater than or equal to that power one, or the exponential one. This right here means liquid. And I need my liquid output and plot as blue. Else if this user point is less than the exponential, but greater than that horizontal, which means greater than that horizontal value, which was linear, I found by doing linear EQ I1. In this case, this is mixed. And if it's not in between those two things, then it's below or above. And in both of those cases, this else indicates gas. So I'm going to leave it to you to add in the fprintf statements as practice, just for the different outputs, as well as plotting the specific points based on the color. But now that we have the structure set up correctly, we need to add the repetition. And I want this repetition, so I'm going to add a while loop that has, I might call this, just like flag. I'm going to call this flag is equal to 1. I want this to run as long as this flag is equal to 1. So I'm going to initialize flag is equal to 1. I'm going to have this keep running. I want this, as the program says, whoops, hit the wrong button. Just fixing my indent. The error I was getting, in case you were getting that, is I forgot a parentheses in my integral. But I want this to run until liquid is values entered that's liquid. That means I want this flag to stay at 1. But if one of these points meets the liquid condition, I want to change my flag. I can change it to whatever I want. I'm going to just change it to 0, change and break out of loop. You could use a break, but this is a better approach. Change this flag value. That way, when it comes back around, it won't enter this loop again. So in some way you could also check and just say while you could store the color, have a certain value associated with each. There's a lot of different ways to do it. The easiest way for me is to think, okay, I want this to always keep running while this value is 1. The only thing that's going to change this value is when we get to the liquid phase. So like I said, you need to add in your output. You need to add in your plotting of the points, but this gives you the structure that you need in order to not only make a decision for one point, but to keep asking until. So I encourage you to take a look at the sample output. As you add the output to it, you'll notice that the sample output doesn't include a lot of the things that it had up here, like the title or the X labels and things like that. You'll see that this stuff is included to help you better understand the problem, but only add the formatting that is required. And it says that no other formatting is required. Additional formatting is shown below for your reference only. So remember to keep that in mind. Don't spend extra time on the final exam doing extra formatting when the main focus is, are you setting up the loops correctly? Are you setting up your if statements correctly? Are you doing the processing correctly?